We discussed about a bipartite graph. Okay, so what is a bipartite graph? A graph, if in a graph, if you can partition the vertex set into two sets such that no two elements in the first set are adjacent and no two elements in the second set are adjacent. Okay, and if at all there is an edge connecting two vertices, the first vertex must belong to the first one end of the edge must belong to the first set, other end of the edge must belong to the second set, like this. So if such a if such thing possible, then the graph is said to be a bipartite graph. Otherwise, it is not a bipartite graph. Okay, so we have seen some examples in yesterday. Okay, so let me bring this here. Okay, so we have seen some examples yesterday. We were able to identify this graph as a bipartite graph because I can make the actually this must be u1 u2, right? Okay, because we were able to partition this set vertex set into two sets such that no two vertices are adjacent in the respective sets, and therefore it is a bipartite. Therefore this can be called as a bipartite graph because we were able to partition the vertex set into like that. Okay, now if I see like this, okay, now you are not able to partition two sets like this. Okay, because whatever the partition you take, there is always a pair of vertices which are adjacent in that partition. Okay, so that is not possible. Whereas if you take like this, let us say like this, A, B, C, or let me call it as U1, U2, U1, U2, U3, U4, U5, U6. Now, can you say whether it is bipartite graph or not? Can you identify whether it is bipartite or not? If I want to make it as if I want to call this as a bipartite graph, I should be able to make a partition on the vertex set such that no two vertices in the first set are adjacent, no two vertices in the second set are adjacent. So can I do?
No, sir.
No. See once. You take U1. Okay. You take so because U1 is neighboring to U6 and U2. So you take U3. If I take U3, then I cannot take U2 and U4. I can take U5. Am I right?
Yes, sir.
So if I put like this, then remaining things are U2, U4, U6. Okay. Now are these two adjacent? U1, U3 are not adjacent, and U3, U5 are not adjacent. U1, U5 are also not adjacent. So this is fine. What about U2, U4? U2, U4 are not adjacent. And U4, U6 are not adjacent. U2, U6 is also not adjacent. Okay, so is it not bipartite? Is this bipartite or not? So U1 to
It is, sir.
U1 to U2, you see here U1 to U2, U1 to U6, U3 to U2, U3 to U4, and next U5 to U6, and U5 to U4. See, these two are same graphs. Don't think that just remove this. Okay, if you want, you just remove these circles. These two are equivalent graphs. Okay, don't say that this graph is different from this graph. These two are, you can draw the graph n number of ways. Okay, shape of the graph is not important. How they are connected is important. Do you understand? Whether graph is looking like this or looking like this, it doesn't matter. As long as you are giving the connecting the vertices correctly. Okay, so why you are able to do like this, and why you are not able to do like this, and why you are able to do like this? If you observe, this is a cycle. What is the length of the cycle?
4.
4. So is it an even cycle or odd cycle?
Even cycle.
Even cycle. What is the length of this cycle? 1, 2, 3, 4, 5, 6. 6. Therefore, is it an even cycle or not?
Yes.
Yes, sir.
Okay, so in these two cases, you are able to make this into like this partition. But what is the problem here? This is not a cycle. This is a graph. But graph is containing a cycle. Am I right? This is one cycle. This is another cycle. This is another cycle. Can you see that? Okay,
Yes,
U1.
sir.
But what is this cycle length?
3.
3. What is this cycle length?
3.
So there is an odd cycle present, right? In a graph. So if you see an odd cycle present in a graph, then that cannot be bipartite. Is that okay? Because if I want to, I can put this vertex here. I can put this vertex. Okay. Third vertex is going to make a adjacent vertex with one of these two, either from this vertex or this vertex. As a resultant, you cannot make the the partitions as that no two are adjacent. That is not possible. So that is the result. So what is the result? A graph is bipartite if and only if it is not containing any odd cycle. Okay, if at all there is a cycle present in the graph, that must be of even length, then only it will be bipartite, otherwise it will not be a bipartite graph. Okay,
కొడుతా చూడు నాకు టైం వస్తుంది.
who is this? Okay, so no, so a graph is so what is the result I am telling? G is bipartite. G is bipartite graph if and only if G has no odd cycle. Write it as a note. G is bipartite if and only if G has no odd cycle. If there is an odd cycle, G cannot be bipartite. If there is no odd cycle, that means if at all there is a cycle that will be of even length, that means it is going to be bipartite. Okay, so you may write this as a theorem. Okay, we are not going to prove any theorem here. As I said, this is a semester course actually, but was put in as a unit. So we can only see the concepts and the important properties or results. Shall I proceed?
Yes, sir.
So this is about bipartite graph. Now can you tell me about a tree? So what is, when do you say graph is a tree?
When the vertices branch out, sir, like there is a root node and there are leaf nodes.
Like this. Hmm? Hmm? Is that what you are telling?
Yes, sir.
So what happens this? If I draw the graph like this, is this a tree?
Yes, sir.
Yes, sir.
Hmm. What about this?
Also a tree, sir.
So what is your understanding of the tree? Suppose if it is like this, my graph is the entire thing, this one.
Connected but without cycles.
So is this connected or disconnected?
That is disconnected. Tree is connected but without cycles.
You cannot say tree. This graph is connected. Is this connected or you are telling about the definition, right?
Yes, sir.
So without cycle, any graph which is not containing any cycle is called acyclic. Okay, so what is acyclic? Acyclic graph means no cycles present in the graph. Okay, and what is connected?
If there is
Every
a between.
every pair of vertices, or you can say every distinct pair of vertices, vertices adjacent or connected or connected. What do you mean by connected? When do you say two vertices are connected? If there is a walk from one vertex to other vertex, then we say those two are connected. Am I right? So what is a tree? A tree is a connected and acyclic graph. Okay, any connected and acyclic graph can be called as a tree. Okay. So now you can draw several trees. Okay, and you tell me some properties of those trees. Okay, so when I say it is acyclic, that means there is no cycle. Okay, so therefore can I call this as bipartite graph?
Yes, sir.
Okay, this is a tree. It is not having any cycle. So if the graph will not be bipartite only when it is containing an odd cycle. Otherwise, it is going to be bipartite only. Here there is no cycle at all. Therefore, every tree is going to be a bipartite. Am I right? So every tree is a basically bipartite graph. Is bipartite graph. Now, how many edges will be there in a tree? You take any tree. How many edges will be there? You count 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. How many vertices are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Am I counting correctly? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 edges are there. Vertices 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay. So can you see that you take any tree, the number of edges is equal to always number of vertices minus 1. In a tree, that is the relation, but any relation will not become a tree. Okay, any graph having this relation will not be a tree. Okay, tree will have this property. If this property is not satisfied, then definitely it cannot be a tree. If this property is satisfied, that may be a tree or may not be a tree. You have to see some other properties. Is it clear?
Sir, could you repeat bipartite?
Bipartite. This is a cyclic graph, no? That means there is no cycle. When a graph will not be bipartite, well, when this will not be bipartite, I'll write an equivalent statement. G is bipartite, G is not bipartite. You know, we have learnt logic also, right? So G is not bipartite if and only if G has odd cycles, negation. Okay, if there is an odd cycle, then only it cannot be bipartite. Otherwise, it is going to be bipartite. Is it clear? Is it clear?
Yes, sir.
So there is no cycle. That means what is the length of the cycle? 0. No cycle means there is no length also. Okay, so if at all, so this will not be bipartite only if it is having an odd cycle. Will it have an odd cycle?
No, sir.
There is no question of talking about cycle. Therefore, there is no question of talking about odd cycle also. So because there is no odd cycle, it is going to be bipartite. Is it clear?
Yes, sir. Thank you.
Okay, so you can just partition whatever the tree you take. You take the node and you put the node which is adjacent to this node in the other vertex. Okay, so in this case you say, let us say this is first node, second node, third node, fourth node, fifth node, sixth node, seventh node, eighth node, ninth node, 10th node, 11th node. Okay, so what I can do, I will put one here. I will put one here. Where I will put two? In the other place, right?
Yes, sir.
And when I put 2, I will put 3. Where? Here. When I put 3 here, where I will put 4? Here. When I put 4 here, I think the sequence is missed out. So this is 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay. So let us draw the graph up to this one. Okay. So then what happens? You whatever the tree you take, okay, that is fine. So when I write 4 here, I will write 5 here. When I write 5 here, I will write 6 here. When I write 6 here, I will write 7 here. Now you see. So 1, 2, 2. Okay. It's taking time. 1 to 2, and 2 is connected to 3. 3 is connected to 4. 4 is connected to 5. 5 is connected to 6. 6 is connected to 7. And in this set, no two vertices are adjacent. In this set, no two vertices are adjacent. Therefore, this is a bipartite graph. Do you agree? These two are same. Therefore, every tree is a bipartite graph. Am I right?
Yes, sir.
Right. So, what is the next property you can think of? Every tree is a simple graph. Okay, tree is basically a simple graph. It cannot be multi-graph. If this is a multi-graph, what do you mean by multi-graph? There are either there is a loop. Okay, loop means what? Or there is a multiple edge. Okay, there is a multiple edge. Okay, then cycle is there. Okay, then that is violating this condition, right? The graph tree should not have cycles. Okay, if there is a loop or multiple edge, that will form a cycle. Therefore, it cannot be called as a tree. Therefore, basically, tree is a simple graph. Tree is a simple graph, and tree is a bipartite graph. And the number of edges in a tree is always equal to number of vertices minus 1. What else I can say? Okay. And what can you say about edges? What kind of edges they are? Can you see? Observe these edges and tell me. If I remove this edge, what happens? How many components you are seeing now?
2 components, sir.
So what is that edge called? Edge.
Cut edge.
Cut edge. Remove this. Disconnected, right? Therefore, it is a cut edge. If I remove this, disconnected. If I remove this, sorry. If I remove this, I think. If I remove this, again disconnected. If I remove this, this is disconnected. If I remove this, again it is disconnected. That means in a tree, every edge is a cut edge. Do you agree? Every edge is a cut edge. So if you find any edge is not cut edge, that cannot be called as a tree. Every edge is a cut edge. Okay. What can you say about vertices? Can you think of vertices? What do you mean by cut vertex? If you remove that vertex, if that becomes disconnected, then that is said to be cut vertex, right? So in this, which vertices are cut vertices?
All vertices except the leaf, like
Leaf.
the end vertices.
So from that, what is your observation? Which vertices will be cut vertices? The degree is at least 2. Am I right? If the degree is 1, it cannot be a cut vertex. Degree 1 means leaf. Even if I remove this vertex, if I remove this, I remove this vertex means automatically edge is also removed. And it is not disconnected, it is connected again. Still it is connected. Okay. But whereas if I remove this, if I remove this vertex, so that these two edges are also gone, it becomes disconnected. Therefore, it becomes a cut vertex. That means all vertices having minimum degree 2 are going to be cut vertices. Okay. So you please verify exactly 2 or greater than or equal to 2. I think exactly 2, right? Greater than or equal to 2, not equal to 2 also works. Okay. So if it is only node of a single degree, that cannot be a cut vertex. Okay. Then yeah, that's what it is telling. Okay. If degree of v is greater than or equal to 2, sorry. So if the degree of the vertex greater than or equal to 2, then v is a cut vertex. V is a cut vertex. Okay. So that's one property of tree. Okay. So then what about the formula for the number of components? What do you mean by component? Component is nothing but component is a maximal connected subgraph of G. That is called component. Okay. A graph may be connected or disconnected. Okay. If it is a connected graph, then that itself is a component. If it is a disconnected graph, it will be composed of components where each component is a maximal connected subgraph. Is that okay? So if I draw one graph like this, okay, this itself is a component. This itself is a component. This itself is a graph. Okay, this itself is a graph, single component. But if I draw like this, it is having two components. Okay, this is a maximal connected subgraph of the whole graph. This is another maximal connected subgraph of this whole graph. Therefore, this is one component, this is another component, like that. Okay, so component is the maximal connected subgraph. Okay. And cut vertices and cut edges will increase the number of components if I remove that. Okay. Now, what do you mean by okay? Let us see some properties types. So we have seen okay. So okay, any subgraph of a bipartite graph is also bipartite. Every even cycle is always a bipartite graph. No odd cycle is a bipartite graph. Or even if a graph containing an odd cycle, it cannot be bipartite. Okay, tree is a connected and acyclic graph. Tree properties we have seen. And what do you mean by spanning tree?
Subtree.
It is a subtree. Okay, subtree which contains. What do you mean by spanning subgraph? Okay, so spanning tree means it is a subgraph of a graph. Sorry, I'll write spanning tree. Because what is spanning tree? It is a spanning subgraph. Spanning subgraph. Of a graph G, which is what is this subgraph having properties? Because I am calling it as tree, which is connected and acyclic. Am I right? And what do you mean by spanning? When do you say a subgraph is spanning subgraph of a graph? If both subgraph and the original graph containing the same number of vertices, then that is said to be a spanning subgraph, right? So if I give a graph, okay, how to find out the spanning tree? Okay, so something like this. If I give a graph like this, is there any spanning tree from this? So how many vertices are there? 1, 2, 3, 4, 5, 6. Can we have a spanning tree from this? One, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. So 1 to 2, 1 to 3, 3 to 5. Okay. 5 to 6, 5 to 4. Is it not a spanning tree? Is this a spanning tree? Both are containing same both have containing same vertices, and this is a subgraph. This is a subgraph containing same vertices of G. Therefore, this is a spanning subgraph. This spanning subgraph is a tree. Therefore, it is a spanning tree. Am I right?
Excuse me, sir.
Hmm.
What about edges, sir? 2 to 3.
I'm not taking. What do you mean by spanning? Only condition is on the vertices.
Okay, sir.
Is that okay? So this is one spanning tree. Similarly, can you tell me another spanning tree? So 1, 2, 3, 4, 5, 6. Okay. So then it can be something like this. It can be like this: 1, 2, 3, 4. Like this. Is it not a tree? Is it not a spanning tree?
Yes, sir.
What is another spanning tree? I can draw like this. So in a graph, there can be several spanning trees. Do you agree?
Yes, sir.
Okay. So it can be previously I have taken like this, or I can take like this. So 1, 2, 3, 4, 5, 6. Okay. So it can be like this also. This is another spanning tree. Okay. So there can be several spanning trees in a graph. Now the question is, if it is a weighted graph. If it is a weighted graph, so let us say this weight is 3, this weight is 6, this weight is 7, this weight is 8. Let us say this is 1, this is 2, 4, 6. Then correspondingly spanning tree also will have the weight. Okay, just copy those weights: 3, 6, and this is 2. Okay, and this is 6, and this is 1. So what is the weight of this tree? 9, 9 plus 2, 11, 11 plus 2, 12, 12 plus 2, 18. Am I right? Similarly, what is the weight of this tree? This is a 6, and this is 8, this is 1, and this is 2, and this is 6. So 6 plus 2, 8, 8 plus 8, 16, 16 plus 6, 22. So weight of this graph is 23. Similarly, you have another weight. This is 3, 6, 4, 6, 1. So what is the total weight? 9, 10, 16, 20. Okay, so like that, every spanning tree will have a weight when the graph is a weighted graph. Okay, now the question is how to find out the minimal spanning tree. Minimum spanning tree. What do you mean by minimum spanning tree? The tree which is having minimum weight. The spanning tree. Okay, among all spanning trees, the tree which is having minimum weight is said to be minimum spanning tree, or we call it as MST. Do you understand? Okay, so in a weighted graph, so what is the minimum spanning tree or minimum spanning tree? Minimum spanning tree. Minimum spanning tree. What do you mean by minimum spanning tree? It is a if G is a weighted graph, okay, then a spanning tree with lowest weight or minimum weight is said to be said to be A. There may be more than one, right? Is said to be I've already said. Okay, is said to be the minimum spanning tree. Okay, so now the question is how to find out minimum spanning tree in a graph. How to find out the minimum spanning tree in a graph? That is obviously the graph must be obviously connected graph. Otherwise, you cannot find out the tree. So weighted and connected graph. You cannot get a spanning tree from a disconnected graph. No, that is obvious. Because spanning means that tree should contain all the vertices. So when the graph is disconnected, then you cannot form a connected graph from the tree. So obviously default assumption is it has to be connected graph. That among several spanning trees, the tree which is having the minimum weight is said to be minimum spanning tree. Okay, so there are different algorithms to find out the minimum spanning tree. Popular algorithms are Prim's algorithm. One is called Prim's algorithm. And other one I forgot. Okay, other one is called Kruskal's algorithm. One is called Kruskal's algorithm, other one is called Prim's algorithm. Okay. 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 Now you may ask, sir, will every connected graph will have a spanning tree? Answer is yes. Okay, because if I give you connector graph and ask you to find out minimum spanning tree without knowing there exists such a minimum span, without knowing that there is a spanning tree or not, there is no pointing in searching for minimum spanning tree. Okay, so there is a result saying that okay, every connected graph contains a spanning tree. Okay, so what is the result? Write down in your notes. So because I already assumed it is a connected graph, so here also I should say I should subgraph of a I think here I don't need to say. Okay, so here. Okay, so G has theorem. G has a spanning tree if and only if G is connected graph. Okay, if every connected graph will have a spanning tree, spanning tree existing means it has to be a connected graph. So that's the result. Now what is our problem? Write down graph theory problem. So problem. Okay, so given a weight, write down the problem in your notes. Given a weighted, obviously and connected. Given a weighted and connected graph, G, design an algorithm. Design an algorithm to find out to find a spanning tree T of G of minimum cost. That means to find out. So that means to find a MST. Okay, of a connected graph, of a weighted graph. Weighted and connected graph. Okay, so there are two popular algorithms. One is called Kruskal's algorithm. Okay, so first write down put this heading Kruskal's algorithm. So as I did yesterday for discuss algorithm, first write down the algorithm, and this algorithm is very easy to implement. Okay, but you write down the algorithm. Okay, in exams you may be asked to discuss or write down the steps involved in Kruskal's algorithm, or you may be asked to write down the steps involved in Prim's algorithm. Okay, so write down the steps. So first algorithm is Kruskal's. I don't know the phonetics, whether it is Kruskal's or Kruskal's. What is that? How do you pronounce it? Kruskal's, है ना? For a minimal spanning tree. Okay. So first write down the steps. Then I will implement this algorithm to a graph. So for tell me.
So in previous example, in the previous example which we
Yes.
if we keep a edge between 4 and 6, will that also be an spanning tree, sir? Instead of any other edge, if we keep a edge between 4 and 6.
If I put an edge between here in the original graph, in the spanning graph,
In spanning tree, sir.
How can you put a edge without there is an edge in the original graph? Because this is basically a subgraph, no?
Definition says that same number of vertices.
Basically it is a subgraph. What do you mean by subgraph? Subgraph is obtained from a graph by removing certain vertices or certain edges, right?
Okay, sir.
You cannot put an additional edge which is not there in the original graph.
Okay, sir.
Is that clear?
Yes, sir.
If the original graph is containing an edge like this, then either you take this edge or you take this edge. If you take this edge, don't put this edge or don't put this edge, because that forms a cycle. Tree should not have a cycle. Either you do like this or you do like this, so that this becomes a tree. Is it clear?
Yes, sir.
Okay. So now write down the Kruskal's algorithm for minimum spanning tree. Okay, so what is the input? Input for your algorithm is a weighted, I think connected graph is the default assumption, I guess. I think my professor did not mention it as connected. I think that is the default assumption, but I am writing this. A weighted connected graph. Because only connectedness will guarantee the existence of spanning tree. Otherwise, it will not. Okay, so a weighted, I will say, and connected graph. Weighted connected graph. Okay, so what is the output for this? What is the expected output you want? A minimal spanning tree. Minimal spanning tree of G. Okay, so what is the step 1? Write down the step 1. Okay, my professor name is Chowdam. Okay, he is a graph theory specialist. You can Google Chowdam. So input is step 1 is select an edge. Okay, write down, just to write down the words, then we will see. Select an edge. Select an edge, say E1 of minimum weight in G. Of minimum weight in G. Okay, identify the edge. Among all the edges, you identify the edge which is having minimum weight. Okay, so that is the edge that you have to select. Step 2. Okay, having selected, write down. Having selected k minus 1 edges. Okay, say E1, E2, and so on, Ek minus 1. Select the edge. It's most of the algorithms like induction type, mathematical induction type. Okay, so that's why we initialize with one stage, and then we will take this to the kth step, and then we'll go to the k plus 1th step. Okay, so k minus 1, just say we can select the edge. Select an edge. Select an edge. Select an edge. Say Ek. Select an edge Ek. From what edges? From the remaining edges. From the remaining edges means what? The edge set. Okay, that means E of G minus E1, E2, and so on, Ek minus 1 from the remaining edges, subject to the following conditions. Subject to the following conditions. Okay, so what are the conditions? Can I go to the next page? Did you copy? Shall I go to the next page?
Yes, sir.
Okay. So what are the conditions? First condition is, so you can select the new edge subject to the following conditions. The first condition is the edge induced subgraph. The edge induced subgraph. That means E1, E2, and so on, EK minus 1 and EK has no cycles. That means because of the attachment of new edge, because of the attachment of this new edge to the existing edge set, that should not have a cycle. If there is a cycle, if there is a cycle forming because of this, then don't select that edge, because basically we are trying to find out a tree. Okay, tree should not have a cycle. That's why if whatever the edge you are selecting, first condition is that the edge should have a minimum weight. And after selecting the minimum weight, if that minimum weight edge you are trying to attach to the existing edges, if that is becoming a graph containing a cycle, then don't take that. Then you go for the next lowest next best edge. Okay, there's no cycle. What is the second condition? Among all the edges, E belongs to, okay, E of G minus, what is E of G? Edge set of the graph, minus E1, E2 and so on, EK minus 1. Okay, such that E1 and so on, sorry, E1, E2 and so on, EK minus 1 comma EK should become acyclic, and EK has minimum weight. Okay, minimum weight. Okay, so whatever the edge you are selecting from the rest of the edges, after selecting K minus 1 edges, remaining edges are there in this set. Okay, you select an edge of minimum cost so that this becomes acyclic. Okay, then what is step 3? Stop when step 2. Okay, I think that is the reason why my professor did not assume connectedness. Okay, stop when step 2 cannot be implemented. Okay, okay, if you cannot implement the step, means there is a cycle. Okay, okay, or stop after selecting mu minus 1 edges, because a tree with n minus 1 edges, okay, where n is the number of vertices, becomes a graph with a acyclic graph and connected graph, and having n minus edges is going to be tree. Okay, so I think yeah, that's it. So if this is the case, if you cannot implement further, means that is possible only when for a general graph. Okay, if it is a connected graph, you will stop the criteria only with this. Definitely, because every graph is going to have a spanning tree. Okay, so this case will not come into picture if our G is just a graph. Okay, and this will come into picture only our graph is just a graph, but this will not come into picture if you are assuming our the graph is a connected graph. Okay, so if I say connected, I don't think this is necessary. I think you can erase this. This you can erase. Okay, stop after selecting n minus new minus n edges. This is correct, definitely, because spanning tree will contain n vertices, where n is the number of vertices in the original graph, and that tree will definitely contain n minus edges. So this will work. Okay, so did you copy this? So step 3, write only this sentence. Don't write any other thing. That is not necessary. So shall we implement this algorithm to one graph? May I proceed?
Yes, sir.
Okay. So draw this graph. All of you draw this graph. 1, 2, 3, 4, 5 vertices. 1, 2, 3, 4, 5 vertices. Okay, so something like star. So let us call these vertices as something like u1, u2, u3, u4, u5. Now you assign edges, edge weights. 1, 2, 6, 7, and this is 10, and this is 4, and this is 3, and this is 4. Okay, and this edge weight is 8, and this edge weight is 6. Did we cover all the edges? See once. Did I assign weights to every edge or not? Hmm? Did you copy? Let me give some names to edges also. Let me call it as E1. Let me call this as E2. Let me call this as E3. Let me call it as E4, E5, E6, E7, E8, E9, E10. Did I give names to all? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. E10. Is that clear?
Sir, you gave E6 and E9 to the same edge, sir.
E6 and
E9 you gave it to the same edge, U1 to U3.
U6 and U9.
E6 and E9,
E6 and
sir.
E9, sir.
E9. Okay, correct. So this must be. So which one is the other one?
U1 to U4.
4, sir.
Sorry.
Oh,
Let me take black color. U1 to
U4.
U1 to U4. Okay. So this must be what? What is that name? U9.
E9.
E9. E9. Correct. E9. This is E9. I agree. Now tell me with what edge I have to start? Weights are in red color. Edge names are in blue color. So I have to start with
E1.
with minimum weight edge. With which edge is having minimum weight? E1, right? E1 is having only weight 1. 1 is assigned to this edge. Remaining weights are more than 1. So I have to select U1, U2 first, right? So U1, U2, connecting U1 and U2 through E1. Okay. So what is this edge weight? 1, and this is E1. I agree. So what is the next edge you have to select? You select next lowest edge such that when that edge is attached to this edge, that should not form a cycle.
U5, U2, sir.
U5, U2. U5, U2 is having weight 2, and that is the minimum weight when compared to the remaining weight edges. Am I right? So it has to be U5, U2 to U5. This weight is 2, and this edge I am calling it as E7. Okay. Next. So 1, 2 are explored. Remember how many edges we require? There are 1, 2, 3, 4, 5 vertices are there. So I just want only 4 edges. Am I right? To find out a spanning tree. Am I right or not? Is that clear? So
Sir,
what is the
U5, U3 can be connected, sir.
What is the next edge? U5 and
E10,
U5 and
U3.
U5 and U3. You want to select the next least edge, no? So this is 6. But 6 is
U5,
U5 and
U4, sir.
U5 and U4. What is the edge weight?
4, sir.
This you can be selected because 4 is minimum when compared to the remaining edges. Either you select E4 or what is the other thing I can select? E9 also I can select. Can you see that?
Yes, sir.
Okay. But when selecting this kind of edge, if that edge is attached to this, that should not form a cycle. If that is forming a cycle, don't select. Is it okay?
Yes, sir.
For example, let me interchange these two. Let us say this is 3. What is this edge? Sorry. Let us say this is. Let us say this is 4. This is 3. Then which one I have to select?
You want
E9,
to
sir.
Necessarily U9 only. Okay. So shall I select that one? This is E7 ID. The E7 ID. The E7. So next this is E9. So when I take E9 is connecting U1 and U4. Okay. So U1 and U4. U4. Okay. So when I'm attaching this to the existing edges, that should not form a cycle. This is not a cycle. So it is acyclic only. So this is called E9. Fine. So far we have 3 edges, but I want exactly 4 edges, so that becomes a spanning tree of minimum weight. So that I can call it as minimum spanning tree. So what is the next edge I have to select? There are 2 edges of same weight, E4 and E5. Okay. So which one I can select?
They'll form cycle, no, sir.
Which one if I select forms a cycle?
Both.
Any one or both?
Um,
If I select E4, what happens?
it will form a
Cycle.
cycle with U4.
If I select E4, then what is the cycle you are telling? Where is the cycle?
U1,
U5 to
U2.
U5 to U4, U4 to U1, U1 to U2, U2 to U5. That becomes a cycle. So I cannot select this edge. Am I right? What about this edge? Can I select this edge? U1, U1, U5.
No, sir.
This also becomes a cycle. U1, U2, U5, U1. This becomes a cycle. Therefore, this is also I cannot select. Though it is of minimum weight, that edge I cannot select because when added that edge to this existing edges, that is becoming a cycle. I don't want cycle because tree should not contain any cycle. So leave. Tell me.
Sir, if we select E4, how it is going to be a cycle, sir?
E4. Shall I draw it?
Yes, sir.
E4. Okay, so this is E4. What is a cycle? You tell me. It's a closed path, right?
Yes, sir.
What do you mean by closed path? Alternating sequence of vertices and edges, where edges are different. Internal vertices are different. Only initial vertex and terminal vertex are same. Start with U5. If I am coming back to U5, that becomes a cycle, no? U5, U5 to U4 you go. U4 to U1 you go. U1 to U2 you go. U2 to U5 you go. You are able to reach to U5 through a closed path. Can you see that?
Yes, sir.
Avana?
Yes, sir.
This is nothing but a drawing like this only. U1, U2, U4, U5. U1, U2. So U1 is connected to U2, U2 is connected to U5, U5 is connected to U4, U4 is connected to U1. Can you see the cycle now? These two are same. Is it not a cycle?
Yes, sir.
Okay. Therefore, you cannot select edge E4. You cannot select edge E5 also. So, these two are exacted. So, what is the next best edge?
E10 or E2, sir?
E10 or E2. So, if I select E10, that forms an edge with E3. Sorry, U3. Okay, so what is its weight? 6, and this is called E10. Or instead of this, I can add these two. Okay, I can add these two also. That forms another spanning tree, minimum span. So minimum spanning tree is not unique. There can be several minimum spanning trees. Okay, so if I take like this, what is this edge? This is called E2. Okay, so I think this should be erased. Okay, so this is what? This is 6. Now what is the minimum weight? So what is the weight of, so when I say this is G, when I say this is T, so minimum weight is going to be
12, sir.
1 plus 6 plus 2 plus 3, 12. Okay, so you take any spanning tree, that weight is greater than or equal to 12. Okay, you take any spanning tree of this graph, that weight is more than or equal to 12. So this is one tree which is having minimum weight. So that is called, this is a minimum spanning tree. Is that fine? Is that okay? Tell me.
So based on the number of vertices, we should take the number of edges, right, sir?
Because tree will have number of vertices minus one edges, no?
Yes, sir.
So how many vertices are there?
5 vertices.
So how many edges are there?
So 4 edges should be there.
You are growing a tree,
Yes,
right?
sir.
So when you
Yes.
are growing the tree, you stop the process of growing the tree, or the tree cannot be grow further after reaching n minus 1 edges. Now at this stage, whatever the edge you add, that forms a cycle. See, you try to add any other you try to add any other edge that will contain a cycle, that cannot be a tree, that may be a subgraph, that may be a spanning subgraph, but that cannot be a spanning tree. Can you see that?
Yes, sir.
That's it. That's why tree will contain only n minus 1 edges, which is connected and acyclic.
Okay, sir.
Right. So I'll just discuss next algorithm, which is also similar and easy, and with that I will start. Okay. So next algorithm is called Prince algorithm. Next algorithm is called Prince algorithm. So shall we remove the condition on connectedness so that I will add this sentence? Okay. So if I don't assume this, okay, so this, which is what my professor wrote, then you add this condition stop. What is it? When step 2 can't be implemented. Step 2 can't be implemented. Implemented further. Or stop, or else. Okay, otherwise. Is that fine? So this is the first algorithm. Again, it is a greedy algorithm, right? This is also a greedy algorithm because it is asking for a minimum spanning tree. So just write one more algorithm and we will stop. Okay. So second one is called Prince algorithm. Okay. So second one is Prince algorithm. Prince algorithm for MST. Prince algorithm for MST. So write down the algorithm. Okay. So again. Yeah. So again, input and outputs are same. Okay. Here also, as discussed in the previous one. Okay. So what is input? Weighted graph. Output is MST of G. Okay. In MST. In MST. So MST of G. So write down these steps. Okay. Step 1.
Sir,
Tell me.
is it just a weighted graph, or
Yeah.
here also it is a weighted connected graph, sir?
Weighted graph only. Here also weighted graph. Okay. So I'm writing the algorithm for a weighted graph only. Previously also we removed the restriction of connectedness, no? You remember? Okay. So select a vertex. Okay, write down the steps. Okay, if you're see here, make a note for a graph. If you are terminating the procedure because of this, okay, then at this stage you count the number of edges. If the number of edges is not equal to n minus 1, that means MST does not exist. Minimal spanning tree does not exist. Is it clear? If G is not connected, if you are implementing this graph just for a graph, we don't know whether it is a connected graph or disconnected graph, but you are trying to construct a minimal spanning tree. Okay, your program is terminated by satisfying one of these two conditions. Okay, and after termination you count the number of edges that are there in the so far constructed graph. If that is equal to nu minus 1, definitely you are successful in getting a spanning tree. If that is less than the nu minus 1, MST does not exist. You show an error message. Okay, if I'm considering the additional assumption that it is also a connected graph, then this case you will never get. This case you will never get. You will definitely reach to this step, so that you will always be successful in getting the minimum spanning tree. Okay, so select a vertex. Select a vertex. Select a vertex. Say V1. Select. Okay, it can be some arbitrary vertex. Okay. Okay, V1 of G, arbitrary vertex of G. Okay, select a vertex, say V1, and select an edge. Okay, so it is two conditions: selecting a vertex, arbitrary vertex, and selecting an edge. Select an edge of minimum weight, which is incident. Which is incident with V1. That means that the edge should connect to V1, which is incident. Which is incident with V1. Okay. Step 2. Okay. Before selecting that one, when I say this is edge, okay, edge will have two ends. One end is incidenting with the V1. Okay. The other end is, let us say, V2. Okay. Now select V2 also. Okay. So after let us say E equal to V1 V2. Okay. Or if I say it is an undirected graph, when I say this is an undirected graph, you may say like this. Okay. Then select V2 also. After selecting V1, first step is you select an arbitrary vertex. Okay. And to this vertex there can be several edges. Okay. And select the edge of minimum weight. Okay, which is incident to this vertex. Okay. Then select the other end of the vertex also, because we want to grow a tree. What do you mean by tree? Tree is a connected graph. So from one vertex you are going to another vertex through an edge of minimum weight. Okay, again from this vertex you will go to another edge of minimum weight. From that vertex you will go to another vertex which is of minimum edge. So like that, if you completing construction after n minus 1 edges, you are going to get a minimum spanning tree. That's it. Okay. Select V2. No step V2, but description must be written precisely, otherwise program may not execute. So having selected k vertices, say V1 V2 and so on Vk, and k minus 1 edges. When I selected k vertices means indirectly I am selecting k minus 1 edges only. When I selected 2 edges means what? 3 vertices are there. If I selected 3 edges means what? 4 vertices are there. Okay. So and k minus 1 edges, say E1, E2 and so on, ek minus 1. Okay, having both ends. Okay, these edges having ends among these vertices. Okay, in this set X vertices set V1, V2 and so on Vk. Okay, that is the complete description. Okay, then select an edge Ek of minimum weight, which is incident with one of these vertices. That's it. Okay, which is of minimum weight in. Okay, that means one end must be incident with one of these vertices. Other end will be in the remaining set of vertices. Okay, Ek of minimum weight in the edge set. Okay, V1, V2, sorry, V2 and so on Vk, and G minus, so that new vertex will come from this set. Okay, so if this is the next edge, of minimum weight, okay, that one end of that edge must be in this set, the other end one must be from this set, its complement set, so that the new vertex Vk plus 1 can be added to this one. Okay, so G minus V1, V2 and so on Vk. That's it. Okay, let
Sir,
tell me.
if we did G minus V1, V2 and so on till Vk, wouldn't there be no vertices, sir?
Why?
Like if we take like one vertex,
we keep
some
track.
Vi from here, sir. So it will be V1, V2 and so on till Vk, and G minus Vi, no sir. Vi being the vertex.
G minus V1, V2 and so on Vk. So let us suppose G is having 10 vertices. Let us say we selected 4 vertices. Remaining 6 vertices will be in here only, no? So far we selected 4 vertices. Let us say we have next remaining 6 vertices in this complement. What is this set complement means? G minus this set vertex set only, right?
Yes, sir.
That's it. Okay, so we are growing a tree. Okay, so that means to say that, okay, that's it. I can understand. You can understand from this. Therefore, the new set vertex would be Vk plus 1. Where this Vk plus 1? Where select Vk plus 1. Where, okay, the edge Ei, Ek is incident with Vk, not Vk, which is incident with Vi. That I can be, this Vi can be one among these. Okay, and Vk plus 1. Where is this Vk plus 1? This Vk plus 1 will be one among this, and this is the edge connecting these two. Okay. Okay. So then, where Vi belongs to V1, V2 and so on Vk, and Vk plus 1 belongs to its complement. That means G minus V1, V2 and so on Vk. So that's it. Okay. Now then. Okay. So what is the step 3? Stop after selecting new vertices. Okay, so Kruskal's algorithm is we are making the count on the edges, and Prim's algorithm we are making count on vertices. Okay, so every tree, every spanning tree will have n vertices. What is n? N is the number of vertices in the graph also. Tree will have n minus 1 edges. Tree will have n vertices. Okay, where n is the number of vertices in the original graph also. Okay. And here also, I think yeah, he must have stopped if it cannot go to the, it cannot grow further. I don't know why he did not assume weighted connectedness. That should be there. Okay. If it is disconnected, you cannot build the graph, right? So stop or okay. And here also go to step 2. Okay. Connectedness should be there. Otherwise, you cannot bring minimum spanning tree. Okay. So again, here also you should say like this: or stop step 2. Okay, as we did previously. Stop when step 2 cannot be. You add this one also. Stop when step 2 can't be implemented further. You better write like this. Okay, so after exiting from the loop, you count the number of vertices with the number of you count the number of vertices in the tree with the number of vertices in the graph. If they are equal, that means you got a minimum spanning tree. After exiting from the loop, if the number of vertices in the tree is less than the number of vertices in the graph, that means you did not get the minimum spanning tree. You did not get minimum spanning tree means the given graph must be a disconnected graph, because for a connected graph definitely you should get a spanning tree, minimum spanning tree. Okay, so connected graph will lead to this, disconnected graph will lead to this. Okay, less than disconnected graph will lead to this, connected graph will lead to this. That's it. Now we'll take the same algorithm, we'll take the same graph and try to implement Prim's algorithm. May I proceed?
Yes, sir.
Okay, so because I changed the edge weights, let me copy and paste the same thing instead of the graph from the book, my notebook. Let me copy and paste. Okay, so this is the graph, no? So that spanning Prim's, even if you apply Prim's algorithm, what should be the weight of the MST? 12 only. That may be minimum. That may be a different spanning tree. But that minimum spanning tree also should have same weight. If you are getting more than 12, that means our algorithm is not correct. We did somewhere mistake in the algorithm. Let me copy like this. Okay. Now you have this graph. Now let us apply Prim's algorithm. So we can start with any arbitrary vertex. Now tell me with the vertex you want me to start.
Sir,
Among
U5.
U1, U2, shall I start with U5?
Yes, sir.
So this is U5. Now how many edges are incident with U5? E5, E7, E10 and E4 also. Among 1, 2, 3, 4 edges, which edge is having minimum weight?
E7, sir.
E7, right? So you select this edge. So this is U2. This is U2. So this edge is having weight 2 and this edge name is E7. Okay, now this is my second vertex. Now from this vertex you see which edges are incident with this one. Okay, so that is what our algorithm says, right? Okay. Right, the other vertex must be in the rest of the things, right? So now you tell me what are the edges which are incidenting with this one.
E1,
Not
E8.
only U2, you can say you have to observe U5 also.
Okay, sir.
Okay, you identify the edges which are incident in with U2, you identify the edges which are incident with U5. Among all those edges, you select the edge of minimum weight.
E1, sir.
E1, sir.
E1, na? E1 is having 1, that is compared to all other edges 1. So here E1 kuda 4, 3, 3, 3. So I think I should select the next edge as E1. So next E1, okay. So this is weight 1. This is called as E1. Now what is its end? This end is U1. Okay. Now having selected how many edges we want? 5 vertices and 5 vertices we want. Already we reached up to 3 vertices. Okay. Now you see the edges which are incident with these 3 and select an edge which is having minimum weight. Okay, so that one end is in this, one end of the edge is in this set, the other end of the edge is in the complementary set. That means in the remaining U3 and U4. Okay, remaining is what? So as of now U1, U2, U3 is there. Next one is sorry, U1, U2 and U5. Next one is what? U3 and U4. You select an edge. Okay, one end is among this, one end is among this, and that is of minimum weight. So
E9, sir.
E9, E9, E9 is having weight 3, and that 3 is lesser than all other weights, and 3, one end is U1, fine. The other end is in U4, that is also fine. Therefore, I can select E9. So this is E9.
About E7.
Huh?
E7.
Where is E7? E7 we already selected, right? First edge itself E7. Can you see that?
Yes, sir.
So now this is E9. This is E9. Okay, what is its end? U4. So this is also now joined with this U4. Okay, so what is there? You are having only U3. Now you select an edge of minimum weight such that one end is one among these and other end is U3. That means U3 is here, and so which one is with minimum weight?
E10, sir.
E10.
10.
Where is E10? E10 is having 6, and this is incidenting with 10. And you can take E10 Or you can take E2 also, no? You see here,
Yes, sir.
I can select E10 or E2. Alright. So if I select E10, E10 is connecting E5 and E3. Okay, E5 and E3. So this is E10. This is E10. You can see this is not cyclic. This is not containing any cycle. You can see here. Okay. So what is its weight? 6. Now all the vertices are got 1, 2, 3, 4, 5. 5 vertices we obtained. What is the weight?
12.
Is it 12? One plus 2 plus 3 plus 6. One మర్చిపోయానా 1 plus 2 plus 3 plus 6 అంతేనా 5 vertices 4 edges అంతే 9 10 12. So we got it. So whether it is the Prince algorithm or Kruskal's algorithm, we are able to find out minimum spanning tree. That means a spanning tree of minimum weight. So spanning tree need not be unique, but value of the spanning tree, minimum spanning tree is going to be unique. All the minimum spanning trees will have same minimum weight, which is 12. Okay, so these two are very important in examination point of view. You can expect one problem of this type. Finding minimum spanning tree on using Prince algorithm or Kruskal's algorithm. Is it okay?
Sir, in the exam, they will be asking even to write algorithm as well, sir.
Yeah, they may ask you to write the algorithm. Okay.
Sir, should we also write steps we followed?
No need. That will be tedious procedure. No, you write the algorithm and you implement the algorithm and get this step. You don't need to show step 1 is this graph, step 2 is this graph, step 3 is that graph. If you do that, that will be very nice. That will be very good. So that the evaluator will understand how you got this. That may be better, I guess, because if I'm evaluating, I can understand. But if the paper goes outside, we'll discuss that when the recording stops. Okay. So I'll just discuss a few more types of trees so that this discussion on trees will be over. So we discussed about minimum spanning tree. We discussed about tree and its properties, spanning tree, minimum spanning tree, Kruskal's algorithm, Prince algorithm. Now what is directed tree? You just see the definition. Okay, directed tree can also be called as a poly tree or singly connected network or a oriented tree. Okay, so it is a directed acyclic graph. Okay, it is a directed acyclic graph. Okay, so that means previously we discussed about undirected trees. Okay, now this is a directed tree. That's it. In other words, if you replace the if you just ignore this directions, if the resultant graph is a tree, then that is said to be a directed tree. That's it. Is it okay? In a directed graph, ignore the directions, then that becomes a undirected graph. If that undirected graph is a tree, then the graph is said to be directed tree. That's it. Is that clear? What do you mean by tree connected and acyclic? May I proceed? And I copied this definition from Wikipedia. You can Google it. May I proceed?
Yes, sir.
Okay, so next one is a binary tree. Okay, so binary tree is what? Binary tree or graphs are tree data structures where each node has up to a possible 2 branches are called children. Okay, these are all called left branch and right branch, or left child or left right child. Okay, it can have at most 2 children, not more than 2 children. Okay, so this is called left child, this is called right child, left branch, right branch. Okay, so this is having 2, this is having one child, one left child, one right child, this is having one left child, one right child, one right child, and one left child. Okay, such a trees are called binary trees. The trees were having at most 2 children. Is it okay? And what is an external node? External node is the one without any child branches. So in this, what are the external nodes? I think
1, 4, 7, 13,
I
sir.
think this also must be external node. No, this is also not having any child branch. Am I right?
Yes, sir.
So this also must be marked in red. So 1, 2, 3, 4. These 4 must be external nodes. And here 1, 4, 3, 7. These are all external nodes. Am I right? Okay, so this also must, I'll delete this. Okay, so these are all the external nodes. Okay, and the size of a binary tree refers to the number of nodes it has. So what is its size? 14, I think. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 is the size of this tree. Okay, that's it. So these are all the concepts in trees. Okay, so if you can see the syllabus. Stop recording.